So thank you for the introduction. So I'm Leonardo Fallani from University of Florence. And first of all, let me thank Gediminas for bringing me here. So I'm really enjoying this conference, and so I'm really honored to be here in front of you. And so today I will tell you about some recent work that we performed in Florence about controlling quantum system and engineering new kinds of quantum system with fermionic ultra-cold atoms. So let me give a very brief introduction, and just to highlight the fact that in cold atom physics, and we have already heard that in several talks already, so we have very nice tools for controlling, for example, the motion of the particles. For example, we have optical lattices, and we have heard about them, that allows us to bring a natural connection with the world of solid state, because these atoms trapped in these standing waves of light exhibits most of the physics of electrons in real materials, but with some nice features. For example, the fact that on the one hand, on the quantum simulation side, you can really implement some exact or almost exact implementation of interesting condensed matter models. And on the other hand, this possibility of controlling the state of atoms allows us to achieve some kind of new extreme states of matter, so achieve some range of parameters that cannot be achieved in conventional materials. And in doing that, so what we are mostly interested in is in the possibility of controlling the internal state of atoms. Because remember that each of the atoms that you are trapping in optical lattice is a very complex object with a lot of protons, neutrons, and electrons. And so in principle, you can have access to several internal states, several degrees of freedom. And this is what we are focusing our activity in my group in Florence. And for this particular reason, we are studying ultra-cold gases of 2 electron fermions. So these are ytterbium atoms that have some nice property. And in particular, one of these nice properties is the fact that you can have access to a quite large internal Hilbert space. And in particular, you can have access to two different degrees of freedom. One has a nuclear spin degrees of freedom, in which the spin comes from the nucleus of the atom. And since the nucleus has spin 5½ we can access a 6-spin manifold in the ground state of the atoms. But in addition to that, we can also access a different degree of freedom, so we can have electronically excited states. And I will come to this point in the second part of my talk. And from this control of internal state of the atoms, we can study new routes for the development of quantum simulators or synthetic quantum matter. And this is what we studied in recent years, and what I will tell you today, just one aspect of what we studied, which concerned the physics of synthetic dimensions and gauge fields. So let's start with some older work that we performed in this work in 2015. That is our first implementation of synthetic dimension. And I would like to thank Hannah for the very nice introduction. So she already gave you the flavor of what a synthetic dimension is. So I will not have to spend too much time to convince you that synthetic dimensions are anything to do with drugs or with some synthetic experience. Even if I would like to say that this figure on the cover of this book is quite similar to figures that we also like to sketch in our papers, and Alessio might recognize this figure. And so I'll just remind you what a synthetic dimension is from the experimental point of view. So what do you need to implement that? You just need some quantum states, and you need some coherent coupling between these quantum states. So in our first implementation of that, we were using these nuclear spin states. So in this is the nuclear spin manifold of ytterbium atoms, and we can couple these different spin states by using Raman transitions. Raman transitions were already introduced this morning by Wolfgang, for example. And the idea is simple. So you take 2 lasers with different polarization. And so if you absorb one photon from one laser beam, and then you emit a photon in the mode of a second laser beam, you can induce a coherent spin flip between different spin states. And so the idea of synthetic dimension is very simple. So you have a set of discrete spin states here. You connect them with this coherent next neighbor coupling. And this coupling is coherent. You can see that from these images, for example. These are Stern-Gerlach images, in which we can see the evolution of a spin population starting from just one spin state, then switching on the coupling. You can see as a function of time population going forth and then going back. So this coupling is really coherent at a quantum mechanical level. And if you have that, you can now see that this system is quite similar to what you have in a lattice, in which you can map the spin state onto a site index along a fictitious fourth dimension. And the Rabi coupling between different spin states plays the same role as the quantum tunneling from one side to the next neighbor side of a lattice structure. And at least at the single particle level, the Hamiltonian is the same. So you can write down the same kind of tight binding Hamiltonian. And so you can study the dynamics in this internal space to emulate the physics of the dynamics along a lattice direction. And this idea was pioneered in this work by Alessio and Maciek and co-workers, and really in this first work the focus was on trying to go to 4D, as also Hanna was mentioning before. So again, in addition to X, Y, and Z, so to the three-directional space, you can encode this fourth dimension in the internal state of the atoms. But then it was soon realized that this idea is powerful also because it can bring some complementary techniques to what you can do with ordinary lattices. And so this paper came, and again, Alessio, Gediminas, and Maciek are among the authors of this proposal that was then realized by us and at the same time by the group of Ian Spielman at JQI. So the idea is to study a kind of hybrid system, which is half in the real space, half in this synthetic space. So it's a kind of two-dimensional system. So in real space, you have a lattice. So this is how the system behaves in real space. You have just a string of atoms with different sides, which are defined by the optical lattice. And then you add these Raman beams, which couple different spin states. So if you add this spin coupling term, you can now picture these spin states as these orthogonal fictitious synthetic dimension. And so you now realize that you can obtain a kind of 2D system, or let's say better. So you have a kind of strip of ladder system in synthetic direction. And this idea has some pros and cons, or let's say better, some pros and features. One feature is the fact that naturally, you can couple only a limited number of sides in the synthetic dimension because, generally speaking, you have access to a limited number of spin states. So synthetic dimensions are very good to study ladder physics, so study just systems with narrow extension on this side, and also, as I will point out later, so with very well-defined edges, because you can control the number of sides in the synthetic dimension that you can couple. The very interesting feature is the fact that if you realize this kind of system in the lab, and this is a very simple system because you just need one D optical lattice and then these two Raman beams. And if you do that, you can get an artificial gauge field for free. You can get the effect of a synthetic magnetic field for effectively charged particles. The reason is that the tunneling matrix element in the synthetic direction is a complex quantity, and this comes from the fact that you have to compute the Rabi frequency for this process, and this Rabi frequency depends on the phase of electromagnetic field. So it depends on the relative phase which has been acquired by the two Raman beams at the point of interaction. And this phase will depend on position in real space. So as a consequence, to make a long story short, so if you take a particle that hops around a plaquette of its hybrid lattice, so it will pick up a non-zero geometric phase because the phase which is imprinted on this link is different from the phase which is imprinted on this link. So, and you realize that this provides the analog of a Aharonov-Bohm effect for a charged particle in the presence of a transverse magnetic field. And so by imprinting this phase with this laser, with these lasers, we can reproduce the effect of this artificial magnetic field. So there are several ways to do that in cold atom physics, and this is just one of these, and probably this is technically speaking, the easiest way, because you don't need any kind of super lattice or potential gradient. You just need to apply these two Raman beams. And if we do that, we can study some interesting physics, and the physics that we studied is connected to the physics of edge states. And so in our system, we are realizing something that is similar to the quantum Hall effect, in which you have a 2D electron gas in the presence of a transverse magnetic field. And you know that the quantization properties of this system, so the quantization of a conductance in the quantum Hall effect is a topological effect, and this effect is connected to the presence of edge states which are circulating at the border of a material. And one of the key features of these edge states is the fact that they have a very well-defined direction of circulation, and this comes from the magnetic field which breaks time reversal invariance. So you have these chiral edge currents running at the border of a material. So if we want to investigate this kind of physics in our very minimal ladder realization of this kind of system, so you realize that what we have to do is quite simple actually, because if we have some edge current running at the border of our synthetic strip with some direction of circulation that is provided by the direction of the magnetic field, so you realize that since we can have a kind of single site imaging for free along the synthetic dimension, in order to detect these edge currents, it is enough that we see atoms in this spin state going towards one direction and atoms in this other spin state going towards the opposite direction. So we have system of fermions, so naturally if we just perform adiabatic loading of this Fermi gas in this kind of structure, we expect to observe these edge currents, and this is actually what we observed in these first experiments. So these are images of a time of flight, just ordinary time of flight imaging that allows you to detect the momentum distribution function. And you can see that atoms in this spin state corresponding to the upper leg of a synthetic strip move preferentially towards the left. Atoms in this spin state corresponding to the lower leg of this strip move preferentially towards the right. So you have this kind of counter-propagating motion along with the two legs, which is an evidence for these edge currents in our synthetic Hall strip. Then I will not focus on that, but we can also perform some dynamics measurements, some quench experiment in which we prepare a wave packet with some initial with some initial center of mass, and this is the average position in synthetic space and average position in real space, and looking at the evolution of the system as a function of time, we can reconstruct this kind of nice orbits that are reminding of a cyclotron orbit of a charged particle in the presence of a magnetic field. But of course you have here a sharp edge, and so you have a bouncing of these orbits out of this edge, and so this is the kind of semi-classical origin of these edge states that I was commenting before. Now, before telling about some more recent work, I would like to give you just 2 slides of connection between this idea of synthetic space and what happens in real space. So because I've tried to convince you that if you have a system with these spin states which are Raman coupled with this next neighbor coupling, this is equivalent, so we can think to this system in terms of this synthetic dimension, in terms of this magnetic field which pierces this synthetic dimension. But of course we can forget about that for a moment, even if we like to think in these terms, and just think to what happens in real space. So in real space you have just a string of atoms. These are connected with this Raman coupling which induces spin flips. And as we heard from Wolfgang this morning, so if you have a transition which flips the spin with a change of momentum, and the change of momentum comes from the fact that the 2 Raman beams have a different propagation in space, so they imprint momentum onto the atoms, you will have the physics of spin-orbit coupling in a multi-level system. And so if you think in terms of addressed energy band description, so this is similar to what Wolfgang was showing just for 2 spin states. So this is just what you expect if you have many spin states. So here you have the energy dispersion relation, so energy is a function of momentum, so different parabolas. This is the free space case, but in a lattice this would be quite similar. Different parabolas which are separated by the momentum transfer by the spin-orbit coupling interaction, and you have the spin-orbit gap appearing when 2 different energy bands cross. And so you can realize that now, if you take a state which lies within the within the spin-orbit gap here, so this state is made up of 2 spin components. One rightmost spin component moving with positive group velocity, so in one direction, and one leftmost spin state moving in the opposite direction because of a negative group velocity. So you have this counter-propagating spin current in real space that maps onto this chiral edge mode in the synthetic dimension. So there is this nice connection about this physics in the synthetic dimension picture and what happens with a spin-orbit coupled gas. So in my remaining time, so how much time do I have? 6, that's perfect. So I will tell you about some more recent work in this direction, about a different implementation of this idea of synthetic dimension that is quite general. So I would like to tell you about more recent work in which we implemented this idea with electronic state, so, or if you want, how to realize a 5th, very tiny, however, dimension. And I told you previously that in our ytterbium atoms we can access different degrees of freedom. So in addition to these spin states, we can address this electronic state. So atoms can be trapped in these long-lived electronic states, so the lifetime is about 20 seconds. So this can be considered as an additional degree of freedom for quantum simulation. So you have a quite large now Hilbert space, and so there is very nice physics concerning the interaction between these 2 degrees of freedom, but I do not have the time today to talk about that. So, but I would like to tell you about, now let's drop the spin degree of freedom for a moment and just focus on this pure 2-level system. So you have a ground state that is stable and this excited state which is very long-lived. So lifetime is 20 seconds. Nevertheless, you can excite this transition, which is very forbidden by selection rules. And this actually is a transition which is very interesting for people working in metrology, because out of this transition, which is in the visible part of a spectrum, you can realize very precise optical atomic clocks. And the fact is that the frequency is very well defined because of a very long lifetime of excited state. So in order to access this transition, you need to have good lasers, and we are collaborating with that with the National Institute of Metrology in Turin. So I skipped some technical details, but if you are able to have a good laser access in this clock transition, you can achieve, you can achieve coherent coupling between the 2 levels, the ground state and the excited state. Again, you have radio oscillations here for quite long times of hundreds of milliseconds. So you can engineer a coherent coupling between these 2 states. So again, so now you have the situation of a 2-level system which is coupled by a single photon transition now. With a visible photon, so you have momentum naturally. You have a delta K, so you have a spin-orbit coupling, again, for free in this kind of system. And actually, this is quite nice, because this is a system which you have, okay, of course, you can map this ground and excited state onto pseudo-spin 1/2, so minus 1/2 and plus 1/2, and you have this momentum transfer that you can also write in terms of a spin-orbit Hamiltonian. And the nice thing is that you have now a pure 2-level system, so you do not have any problem about intermediate Raman states, so you can suppress any eating by spontaneous emission. And on the other hand, this is even simpler than what I described to you before, because now you have just 1 laser. So if you were good in building this very precise clock laser, so now it's easy to repeat the same experiment that I described to you before, with only difference that now we just need 1 laser to align. So now we have this, in real space, these 1-dimensional strings of atoms, similarly to what I've described to you before. And now we have this clock laser that induces transition between the 2 different electronic states. And again, we can think in terms of this synthetic dimension connecting, but now the synthetic dimension is made just by 2 states. But there is some nice features to the fact that since you have just 1 laser, you can change the angle of this laser with respect to the direction of these 1-dimensional samples. And so in this way, you can change the projection of a momentum transfer along this direction, and so you have a way to easily change the flux of the magnetic field through the synthetic strip. And this is my last slides concerning the results. What we did here is to quantify these edge currents that I've shown to you before as a function now of a magnetic field flux. And so here you have this J, which quantifies these edge currents as a function of a flux. And so what do you see here? So you see that you have initially an increase in the strength of these currents, and this is something that you can expect, because also from a classical point of view, so if you have 2-dimensional systems of charged particles, you apply this magnetic field. So if you do not have any magnetic field, of course, there is no reason why you should have some chiral motion of the particles, because you have a time reversal invariant problem. But then if you start applying a magnetic field, you break time reversal invariance, so you expect to have these chiral currents, and naively, these chiral currents from a classical point of view are related to the cyclotron motion of the particles in the presence of a field. But then what happens? So if you increase the strength of these magnetic fields, so you will increase the strength of these currents, fine. This is something that is easy to expect. But then if you look at the measurements, so what happens? So you keep increasing the magnetic field, you observe a reduction of these currents. If you keep increasing more, so these currents change direction. So from the point of view of classical electrodynamics, this is strange. So this is a right-hand rule becoming at some point a left-hand rule. So the reason why we observed that, I think that this is clear to most of you, but I'd like to tell you nevertheless. So the fact is that First, this happens at very large magnetic fields compared to what you can get in conventional materials. So the effective field here is about 10 to the 4 Tesla. And this happens also because your system is defined on a lattice. So we are providing a kind of lattice version of a quantum Hall effect. And so if you have a lattice, you have a minimal unit of area. You have a minimal unit of area, and what you're doing is imprinting these phases on the links of this lattice structure. And so this means that in addition to this symmetry that you have because of time reversal that tells you that if you reverse the sign of a magnetic field, you should reverse the direction of the currents, you have an additional symmetry because you know that since a magnetic field is a phase, and the physics should be, of course, invariant if you add 2 pi to a phase, you have this additional symmetry which comes from the lattice structure. And the phase 2 pi means 1 quantum of flux. And so if you combine these two properties together, you can realize that the current should vanish at pi flux, so half of a quantum flux, and should be periodic by 2 pi. And very last comment, so just some naive considerations, but of course one could map what we are observing into the physics of a bulk system, and we have heard about from Hannah before about the Hofstadter butterfly spectrum that emerges from this lattice version of the quantum Hall effect. And if we plot this spectrum energy as a function of flux in terms of a topological invariant, which is the Chern number, you can see that the Chern number corresponding to different bands of this energy spectrum changes sign, so for example change from warm color to cold colors as you cross the point of half of a quantum of flux. And because of the bulk to boundary correspondence principle, what happens in the bulk is connected to the physics of the edges. Of course, our system is very finite size, it's just a 2-leg ladder, but at least at qualitative level, so this is connected to this change in the sign of a Chern number. Okay, so I do not have the time to fully discuss the outlooks, but I just tell you that we are working, we are going on this direction on 2 sides. On the first side, so we are trying now to engineer some more complex structure in the synthetic dimension. For example, one interesting possibility that we are implementing now is the possibility to realizing periodic boundary conditions, or the so-called Toblerone lattice, in which we can cancel the effect of the edges and glue the edges together, applying physical periodic boundary conditions when the coupling are in a closed chain. Of course, going towards more complex, interesting ladders or 4D, as Hannah was suggesting before. And very last slide, so what is also interesting now is to study the effects of interactions. And we have heard about different ideas for the implementation of synthetic dimension. Each of them is different when it comes to interactions. And for example, in our case, interactions has a quite funny behavior because they are naturally long-ranged along the synthetic space because these atoms are sitting on the same physical position of space. Nevertheless, you have some kind of very interesting physics that can be studied. So with that, this is the wonderful team that have the honor to work with in the lab. So I'd like to thank all of them and funding agencies, and with that also advertised positions if some of you is interested. And with that, I'd like to thank all of you for your attention.